Here we have a classic rate law or differential rate law problem. They give us an equation at the top, and in that equation there are only two reactants. Those are the only two things that will determine the differential rate law, unless there's something else called an inhibitor or a catalyst, but let's not worry about that for now, just the two reactants. So the general format for a differential rate law is that it's equal to, a rate is equal to some rate constant K times the concentration of the first reactant raised to some power X, which we'll find out, times the concentration of the second reactant raised to some power Y. We want to know the values of X and Y. That's important. And in order to find that, we have to look at the data table that they gave us. So they gave us a whole bunch of data, 5 experiments with initial concentration of iodide ion and initial concentration of H2O8 along with the rate. Let's do this using the eyeball method. I think this is a lot faster and simpler than trying to do something else. So first of all, let's look at experiments 1 and 2 only. Notice that in comparing experiments 1 and 2, the concentration of H2O8 remains the same. The concentration of iodide gets cut in half if you're going from experiment 1 to experiment 2. Or if you're going the other way from experiment 2 to experiment 1, it doubles. The rate, what happens to the rate? The exponent for the rate is the same. So comparing 12.5 to 6.25, you'd have to say, well, 6.25 is half as much. So in eyeballing this, what I'm going to do is go from experiment 2 to experiment 1. I'm going to say, aha, upon doubling iodide concentration, the rate doubles. The only way for that to happen is if the value of X, the exponent for iodide, is 1. Let's look at, I'm going to pull out a couple of experiments and then rewrite the data table so they're right next to each other. Let's compare experiments 1 and 3. So in experiments 1 and 3, I'm just going to rewrite, just jotting down these two experiments so that we can see it a little more easily. I'm going to rewrite the data table down below. Just looking at runs 1 and 3. And let's do a similar eyeballing as we had done above. Notice that iodide concentration stays the same, but H2O8 concentration does change. In fact, if we double the concentration of H2O8, in response, the rate also doubles. 12.5 is twice as much as 6.25. And so we can conclude that the value of Y is also 1. If you can do the eyeballing method, this becomes a lot easier than if you had to go through the mathematical calculation. So then let's glance at the answer choices here. It says determine the rate law or differential rate law. If we know that the exponents are 1 for iodide and 1 for H2O8, and rate always equals K times those concentrations, our only answer choice that matches our data is this one. K times I to the implied first power times H2O8 to minus raised to the implied first power as well. Now let's look at part B. Calculate a value for the rate constant for each experiment and an average value. So now that we know that the rate is equal to K times iodide concentration to the first times S2O8 concentration to the first, let's start using the data from the table and plug in. So for run 1 or experiment 1, we can say that the rate, 12.5 times 10 to the negative 6th, which I'm getting directly from the data table, is equal to some rate constant K, which we don't know, times the concentration of iodide in experiment 1, which is 0.08, raised to the first power, times the concentration of S2O8, which is 0.04, also raised to the first power. If we crunch those numbers on a calculator and solve for K, K works out to be 0.0039. That's for run 1. Run 1 and run 2. Now let's go on to run 2. The rate, 6.25, 10 to the minus 6. That's equal to some constant K times the concentration of iodide in run 2 is 0.04. And the concentration of S2O8 also 0.04. Let's pull out a calculator, and when you solve for K, this time it's the same, 0.0039. That's curious. Let's keep plugging in. Run 3. The rate is, again, 6.25, 10 to the minus 6th. That equals some constant K times, if we look at these concentrations, 0.08 for iodide and 0.02 for the S2O8. Pull out a calculator and solve, and you get 0.0039 again. Let's try run 4. This time the rate is 5 times 10 to the minus 6. Concentrations of 0.032 and 0.04. Let's plug those in. Pull out a calculator. And are you seeing a pattern here? The rate constant is constant. Run 5, plugging in the numbers from the data table. The rate, 7 times 10 to the negative 6. Concentrations for iodide and S2O8 of 0.06 and 0.03. Pull out a calculator and you can probably guess the value of K is still 0.0039. This is an exercise that they have you do to really impress upon you that the rate constant shouldn't change regardless of which experiment you're running. And so obviously if the calculated values of K are 0.0039 for all of the experiments, then your average would also be 0.0039.